For the pentagon ABCDE, we need to prove the following. Let us begin. First, we will consider a pentagon with vertices A, B, C, D, and E. We begin by first considering the side AB and converting it to a vector going from A to B. Next, we consider the side BC and represent it with a vector going from B to C. Then we have the side CD with a vector going from C to D. Next, we have the side D with vector going from D to E. And finally, we have the fifth side EA with a vector going from E to A. Okay, now what we'll do, we will join vertex A and vertex C, and it's going to be a directed line segment going from A to C. So let's consider the triangle ABC. So in triangle ABC, AB vector added to BC vector, so this will be equals to AC vector. Over here we have used the triangle law of vector addition. Let's label this as number 1. Next, what we'll do, we will join vertex A and D with a directed line segment going from A to D. And now we will be considering the triangle ADC. So here we have AC vector added to CD vector. We have AC vector added to CD vector, and that will be equals to AD vector. Let this be number 2. Here also we've used the triangle law of vector addition. And finally, we're going to consider the triangle ADE. So let's consider the triangle ADE. So here we have AD vector added to DE vector, and this will be equals to EA vector. But here we have to be a little bit careful. This is actually not EA, but it's going to be negative EA. The reasoning behind this is because we started out from point A. This is the initial point, and we ended up at point E, which is going to be the terminal point. So that means the vector law of addition tells us that we need to go from the initial point, the original initial point from A, to the final initial point E. So that means our direction should have been from A to E. However, we are going from E to A, so we have to consider negative EA. So this is going to be number 3. Now let's do one thing. We're going to add all the 3 vectors. We'll add 1, 2, and 3. So this is going to give us on the left hand side AB vector added to BC vector, plus we'll consider number 2, the left hand side. We have AC vector plus CD vector, plus the left hand side of equation 3, so that's AD added to DE. So this will be equals to, now we have AC vector plus AD vector minus EA vector. Now here we can cancel out AD vector from both sides, and we can also cancel out AC vector from both sides, and this is going to leave us with AB vector plus BC vector. So let's write it down. We have AB vector plus BC vector plus CD vector plus DE vector, plus, so we will transpose negative EA vector to the left hand side to get positive EA vector, and this will be equals to 0. But since we are adding a vector, so this has to be a 0 vector, and we have showed that for a pentagon ABCD, AB vector plus BC vector plus CD vector plus DE vector plus EA vector sums up to give us a 0 vector. Now let's go to the second one. Now, in order to prove this, what we'll do, we'll start with the side AB and represent it with a vector going from A to B. Next, we'll consider the side AE and represent it with a vector going from A to E. We'll consider for the vector BC vector, we'll consider the side BC and represent it with a vector going from B to C. Then we have DC vector. So we'll consider the side DC and represent it with a vector going from D to C. And then we have ED vector. So ED vector, we have, we'll consider the side ED with a vector going from E to D. Now, with this direction, we will try to prove the given. So what we'll do, first we will join vertex A and vertex C with a directed vector going from A to C. Again, we will use the triangle law of vector addition. For this, we consider the triangle ABC. So here we have AB vector added to BC vector, that will be equals to AC vector. Let's label this as number 1. Now that means we can combine this AB vector with AC vector with a with BC vector to get AC vector. So that's fine. Now next what we'll do, we will consider AE vector and ED vector. So for this, we're going to join A and D with a directed line segment going from A to D. So we consider the triangle AED. So here we have AE vector added to ED vector, that will be equals to AD vector. So let this be number 2. So this time what we have done, we have combined AE vector with ED vector and made us equivalent to AD vector. And then we're going to consider the triangle ADC such that if we take vector AD added with vector DC, and that will be equals to AC vector. So let this be number 3. And now we add the 3 vectors, 1 with 2 and 2 with 3. And this is going to give us, on the left hand side, we have AB vector plus BC vector plus AE vector plus ED vector plus AD vector plus AC vector, DC vector. This will be equals to, we have AD vector plus 2 times AC vector. We can immediately cancel AD vector from both sides. So let's rewrite everything. So we have now AB vector. We're going to next write AE vector. So these two are done. Followed by BC vector. Then we have DC vector plus ED vector. This will be equals to 2 times AC vector. However, we can see that AC vector is missing on the left hand side. So if we add AC vector on the left hand side, then on the right hand side, we add 1 more AC to get 3 AC vector, and this proves the problem. So we have successfully proved both of the 2 parts for the pentagon ABCD and E.